this is the mean of random variable x. Mu sub x is the mean of random variable x. So, in other words, this variance is, we call this standard deviation squared. This variance is basically standard deviation. And standard deviation is denoted with sigma sub x. This is basically standard deviation of R mu x. So this standard deviation is basically, by definition, square root of this standard deviation is basically by definition square root of the variance of random variable x. So the variance of random variable x by definition is expectation of this function, which is x minus mean of random variable x into the square. And you apply the expectation operator, and when you apply the expectation operator, think of this as g of x. Think of this as g of x. This is constant. Here, what you see here is constant. It's just mean. It is just mean. It is constant. So x minus constant, and then you take the square. So this becomes a function. So if this becomes a function, expectation of random variable of the function g of x is basically, you take summation of x, you take the value of x from the range of x, and then you pass this g of x, and then you know what is the PMF of random variable x. So this is basically PMF, probability mass function, and this is your function. For variance, this function is basically what you see here, x minus mu sub x squared. So it's pretty easy if you understood this formula. See, E z, where z is a function of another random variable, which is basically g of x times PMF of random variable x. So this g of x has a specific form when we compute its variance. Now let's go through another term. You will see in statistics, you will see a lot of times moments, the keyword moment, moments of random variables. So expectation of x, it's called the first moment. First moment, and first moment has a geometric term. First moment, what does it mean physically, practically? It means, this first moment means it is simply mean. It is simply a mean. Second moment is expectation square, expectation of x squared. It is called the second moment. Now, if you apply expectation on the square of random variable, what does it mean practically? It means it is power. You are basically finding the power of random variable x. Expectation of x cubed. This is basically, as you could figure out, it is third moment, and it is called the geometric form. It's basically skew symmetric form. Some geometric shape that you see. So each has a name, and so on. So and so on. All the way you go to x expectation to the n is called nth moment. And I'm not writing it. it says that expectation of x squared and x to the expectation of x to the n are called second and n moments of x respectively. Now we are going to utilize these moments to compute the variance. When we define the variance, it actually utilizes the operator expectation x minus mu sub x squared. Now I am going to quickly write down how I wrote this expression from here. So look, you apply expectation operator on x minus mu sub x squared, which is you apply expectation of x squared minus 2x mu sub x plus mu sub x squared. Okay. How I distribute this operator inside. Look, I have expectation operator on x squared. This becomes the second one. And then minus 2 is constant. You can bring 2 out of the way. And then you apply expectation operator on x. And then you have mu sub x. And then plus you apply expectation operator on mu sub x squared. Okay? You apply expectation operator on mu sub x squared. Now, one conceptual idea that is, okay, I have collected bunch of data, 10, 20, actually 10, 10, 10, and so on. So I have a random variable that actually collected, that I took the measurement, and I see this random variable takes 10, 10, all every time you get 10. I want to find what is the expectation of this random variable. What is the expectation of this random variable? I know that these are just this the random variable, it's just taking constant. So expectation is basically the average, doesn't matter how many measurements you take, expectation eventually is an average. So my point is the expectation of a constant, you can write it down. Expectation of a constant is simply constant. So what you have here is expectation of x, because it is constant, 10, 10, 10, 10. So expectation of the constant is 10. Now this expectation of x squared, we do not know. X is a random variable, we do not know its value. We simply keep it expectation of x squared minus 2. Look, you have mu sub x is a constant. It is simply a mu. Mu sub x is a constant. So constant times this random variable. You can bring this constant out of this expression. So you are left with 2 mu sub x. And then you are left with expectation of x. And then plus expectation of constant square. Mu sub x is a constant. So its square is also a constant. So therefore expectation of a constant square is also a constant. So therefore you get mu sub x squared. Now look, you have expectation of x squared minus 2 mu sub x, and then expectation of x is simply a mu. So this part is a mu sub x. So mu sub x times mu sub x is going to give you mu sub x squared plus you have mu sub x squared. So you have 2 mu sub x squared, negative 2 mu sub x squared, here you have 1 mu sub x squared. So you are left with negative 1 mu sub x squared. And that's how I ask you to find the variance of random variables, you can directly use this formula. You can directly use this formula. So there are some related examples in the textbook. Please practice those examples. And I actually put these examples as part of the homework as well. Conditional probability mass function. I'm not going to cover this one. Ignore this. This is just conditional probability mass function. And basically, a same theory repeats. We want to conditional probability. There are some other properties. These are important before I complete this chapter. So there are some properties of a variance operator. Variance of x plus constant. C is constant. What it is? You can actually write variance. You can distribute this variance operator inside. So variance of x plus variance of this constant. So what is variance of constant? So you have variance of x plus variance of constant is basically expectation of constant minus the mean of constant is also constant. So you have x minus mean of x squared. This is by definition. The C is here, so expectation of 0 is simply 0. So therefore, the variance of a constant, the variance of a constant is 0. So you are left with variance of x. So if you have variance of random variable plus constant, it is simply variance of x. If the constant is multiplied with, if the constant is multiplied with the if the random variable is multiplied with the constant, okay? So if the random variable is multiplied with the constant, if you want to take the variance of constant times x, so see, put this in the form. Okay, by definition, variance of x is expectation of x minus mu sub x squared. So put this in the formula. Replace x with c of x. So we have expectation of cx minus mu sub x instead of x. Instead of x, we have c of x. So expectation of x is mu sub x. Expectation of cx is simply c times mu sub x. So you are left with c mu sub x. You square it, then you are left with this c becomes c squared. So therefore, c squared is a constant. You can bring this c squared out of this expectation. So you are left with expectation of x minus mu sub x squared, which is by definition, this part is variance of x. So you are left with c squared times variance of x. see, there are many examples in the textbook that we are using. There are some homework problems where you will be using this formula type. So variance of constant times x is simply constant square to variance of x. And in the exam, I'm not going to ask you to prove that, okay, show me how variance of constant times x is c squared, a variance of x. You will be utilizing these formulas. You will be utilizing these formulas to solve some numerical problems. So therefore, you may want to just bring these formulas in formula sheet. So variance of a constant is 0, we are given. So variance of constant is 0. So that's all about this chapter. Now in this chapter, towards the end, you see important discrete random variables. Here, all what I did, I summarized all the random variables that we went through in this chapter. We went through binary random variable. We went through binary random variable. Binary random variable has range s sub x is 0, 1, and binary random variable has PMF of random variable x taking value 0. PMF 0 means that its failure probability is q, which is 1 minus q, and 1. PMF of random variable x taking value 1, where x is a binary random variable. It is simply p, where p takes values from, actually it is 0 less than p less than 1. Because if it is 0, p equals 0, it doesn't make any sense. It's a certain event and you know that it's failure or that does not give you anything. So therefore I use 0 less than p less than 1. Where this p is the success probability and failure probability is 1 minus p, which is q. The mean of binary random variable is simply p. Variance of binary random variable is p times 1 minus p. So the mean mu sub x of binary random variable is p, and variance of binary random variable is p times 1 minus p. In other words, it is p times q. I summarize binomial random variable as well. So if we have a binomial random variable, x is a binomial random variable with parameter n, comma p, where p is the success probability, n is the total number of trials. If that is the case, binomial random variable has range s sub x from 0 to n. You can have a toss of a fair coin or toss of a coin n times, and you record the number of heads out of n tosses. Then you can see if the possible values of random variable x is 0, 1, or 2. And the PMF of binomial random variable, see, it's very, very convenient that I summarize all of this in this towards the end of this slide. So you can directly bring this in the formula sheet. In the formula sheet, don't bring trivial formulas to occupy your phone. You are allowed to bring 8.5 by 11. Okay? 8.5 by 11 inches. So unit is very important. So 8.5 by 11 inches front and back. So the PMF of binomial random variable is PMF of binomial random variable x taking value x or taking value k, just to distinguish x and what is an uppercase k, is n k e to the k q to the n minus k. So we know how to determine these combinations. So this is the PMF, and this is the mean of binomial random variable is NP, and variance of binomial random variable that brings my next my slide disappeared from you, so I have to add. So similarly, I summarized Poisson random variable. So Poisson random variable x is a Poisson random variable with parameter alpha. Poisson variable takes one parameter alpha. This alpha is the average number of events happen in a certain period of time. So in Poisson random variable, you don't have in Poisson random variable, you don't have like n number. It could be like just like geometric random variable. Geometric random variable x s sub x. For geometric random variable, it is starts from 1 to dotted dotted. If x is a geometric random variable, okay. So that's why in geometric random variable we derive the mean and mean for geometric random variable. But for for Poisson random variable, Poisson random variables, the range starts from 0, 1, dotted dotted. Poisson random variable, we have PMF. PMF of Poisson random variable is given as such. Expectation of Poisson random variable is alpha, and the variance of Poisson random variable is also alpha. Uniform random variable. Uniform random variable. So we have the range of uniform random variable. We have PMF of uniform random variable, and then we have mean of uniform random variable is L plus 1 over 2, where L is the upper limit, and then variance of uniform random variable L squared minus 1 over 12. Now we are going to cover mean and variance of continuous random variable, which is part of chapter number 4. This continuous random variable will be deriving this sort of form of continuous random variable. Okay? There are some other discrete random variables as well. In the exam, I am going to limit myself to questions to binary random variable, binomial random variable, geometric random variable that I went through, Poisson random variable, and the uniform random variable. So that's all from chapter 3. So this is the summary of chapter 3 that concludes my chapter 3. And based on chapter 3, you will have a complicated experiment that I'm still preparing. I will be planning on posting it today. Now that brings us to chapter 4. So chapter 4 is more important than chapter 3. Chapter 4 is more important than chapter 3. All the theory, you will see many theory. Theory is based on continuous random variable, random variable. Then we talk about discrete. Discrete random variable is basically a special case of continuous random variable. That's why people can add from the probability statistics random processes course, or from the second course on probability. They start with definition like continuous random variable. So chapter 1 to 3 again fundamentals, and this chapter is also fundamental, but for continuous random variable. So in continuous random variable, we start with again one random variable, just like what we did for discrete random variable. So first we learned the notion of discrete random variables, and we learned methods for calculating probabilities and averages for discrete random variables. Here we are going to learn some more generic methods. So So we are going to introduce random variables that can be discrete. Again, I said that discrete random variable is a special case of continuous random variable. That is that we are going to study in this chapter. So mainly we are going to study random variables that could be discrete, that could be continuous, or that could be mixed, discrete and continuous. Mixed type of variable. Then we will learn cumulative distribution function. And it is in Python, they are easy. If you import like from let's say scipy dot stats import, let's say uniform for uniform random variable, you can directly use uniform dot PMF, this function, and you should know that the parameters, what parameters it takes, and you can directly use uniform dot, we are going to study cumulative distribution function, CDF, guys, very important. We are going to study cumulative distribution function, so you can write uniform dot CDF. It's called cumulative distribution function, and we will be studying probability density function, PDF. Cumulative distribution function CDF, we'll study probability density function, PDF. So again, uniform dot PDF, and there are, you just pass some arguments. You take, you see what arguments you take. So you just need to know how these CDF, PDF, PMF work. Then numerically, you can directly use the packages that we have. The packages that we have in Python, in statistics package, you can directly use these functions, PMF, CDF, PDF. And once you determine PMF, CDF, and PDF, CDF is cumulative distribution function, and PDF is probability density function. Once you determine these probability distribution functions, you will be able to determine the probability easily. So you don't have to rely on actual outcomes. You don't have to rely on actual outcomes or word outcomes, for example, tail, things like that. So we will be learning mainly these four topics. So we'll be learning random variables that are discrete, continuous, mixed type. We'll be learning cumulative distribution function, and we'll be learning probability distribution function for random variables, for continuous random variables, and you'll see that this PDF is only applicable for continuous random variables. But the CDF that we'll be running, that could be applied to both continuous and discrete random variables. And then we will study methods for calculating probabilities and averages. Now, in this chapter, I will be introducing new symbols, new notations. Make sure I have most of the notations written in theory, but how I utilize this notation, guys, very important. How I utilize this notation to solve some numerical problems. That is important. So therefore, the solution of the examples that I go through, make sure you at least write the solution of the examples that I go through. Theory you don't have to write, because I already wrote enough theory. You have enough information that you should be able to understand. But there are some solutions that author has provided solution as well. But I made these notes after compiling several years. So make sure that these notes easy to understand. Make sure you take the solution that I'll go through in class. It's going to be less confusing and easy to understand. So first, we talk about, we already know what is random variables. We define the random variables here. But from that random variable, we define a set. So you see that set basically consists of a bunch of outcomes, and we pass this outcome to this random variable, and it has to be less than or equal to b for all b in the real life. So we are talking about b for the entire real life. Minus infinity to plus infinity, so this is entire real life. So b can take any value as long as it satisfies this condition. So b can take any value. But what is the point that if b is the entire line, what is the point you have here? So you will be clear in a moment why I have this less than or equals, because this less than or equals symbol, this inequality will be using to determine the probability. Now our first topic for this chapter starts with this CDF, cumulative distribution function. Make sure you know from now on we're calling it CDF. So you should know what is CDF, cumulative distribution function. The CDF of random variable x, we denote it with uppercase x, uppercase F, F, and then subscript is the random variable, and this subscript random variable can take any value x. It is actually by definition will give you the probability of random variable x less than or equals x. By definition, this cumulative distribution function will give you probability of this random variable x can take any value less than or equals x. Now this x can take any value from the entire real line. So in other words, this f sub x is a mathematical function that can take any value from negative infinity all the way to positive infinity. Any value in the argument that can take from negative infinity to positive infinity. So because x can take any value from that value. So when I talk about CDF of a random variable, it is basically a continuous function that can function of x that can take any value from negative x to negative infinity to positive infinity. Now, can you guys tell me what's the difference between this CDF and PDF? CDF and PMF as we know in our last chapter. PMF, probability mass function. Probability mass function was for if this is PMF of random variable x taking value x, probability mass function took values at certain values of x, right? You remember? Probability mass function is applicable for discrete random variable. But cumulative distribution CDF is a continuous function that can be used for both discrete and continuous random variables. Very important. So CDF is more generic version of PMF. So you don't have to use PMF to determine probability. If you know CDF, then you are set. You should be able to determine the probability for both continuous random variable and discrete random variable. Now let's see how it works. This is the definition, guys. I will be using this definition from now on. So probability, the CDF of random variable x taking value x is by definition it is probability that random variable x takes value less than or equals x. And it is basically less than or equals x less than or equals x is basically an event that corresponds to a set from the sample space. So this is basically the event. So make sure you know. Now I've been talking about the CDF. Let's go through one example. Actually, this example is a part of actually this example. So here a fair coin is tossed 2 times and the sequence of heads is noted. Let X denote the number of heads, find the CDF. Now, in the following example, let X be the number of heads in 3 tosses of a fair coin. Find the CDF of it. I am going to solve this example. So this is more rigorous than tossing a coin 2 times. So it's just increasing the toss one more time, that's all. So, and I will be utilizing the result of this example in the following problem. So that is the reason I will be using this. So let's solve this example. So let X be the number of heads in 3 tosses of a fair coin. Let X be the number of heads in 3 tosses of a fair coin. Find the CDF, cumulative again. CDF, cumulative distribution function. CDF of random variables. So we'll have computer experiment, computer assignment for that corresponds to this CDF. We'll have this computer experiment, computer assignment. But computer assignment, you just simply you identify the range of a random variable, you identify the type of random variable, you just type the random variable, the distribution of the random variable, uniform, binomial, I don't know whatever random variable it is, you just type dot and then CDF. It will give you CDF, okay? But you will have to know what's going on inside this function. People have implemented this CDF. So make sure you solve this example with me, guys. That way you know what's going on, including the diagram that I will go through. That diagram you will not find in the book. So let's now relate this random experiment all the way to the sample space. So let X be the number of heads in 3 tosses of a fair coin. Yes, solution. What is the sample space?
S equal to 0, 1, 2, 6.
Sample space, not the range. Sample space. So let X be the number of heads in 3 tosses of a fair coin. So you toss a coin 3 times.
1, 2, 3.
No. Sample space is again T
Oh, yeah.
T H T H T T H H H T T H T H H H T H H H, right? 1, 2, 3, 4, 5, 6, 7, 8. That's the sample space, right? Now we define the random variable already. So let X be the number of heads in 3 tosses of a fair coin. So let's find range. The range of X, we denote it with S sub X is 0, 1, 2, 3. So number of heads could be in 3 tosses of a fair coin. Number of heads could be 0, number of heads could be 1, number of heads could be 2, number of heads could be 3. Okay, what sort of random variable it is? Is it a binomial random variable? Is it a binary random variable? Is it a Poisson random variable? Is it a geometric random variable? Is it an uniform random variable? What sort of?
Is it binomial?
Binomial random variable. Binomial random variable. Binomial random variable takes 2 parameters. One is the total number of trials. Here, how many? What's the total number of trials?
6.
So So n equals 3, comma, and binomial random variable takes another parameter, which is the success probability. What is the success probability here? P is the success probability. Which is the success probability? It is 0.5, which is 1 half. These are the two parameters that you pass when you use binomial random variable in Python. Now, to find the PM, to find the CDF, what you will need to do, because it's a discrete random variable, you first find the PM. First find PMF of discrete, you know that it's a discrete random variable, discrete binomial random variable. So now PMF of this random variable E sub x taking value 0, k equals 0, taking value 0, this is k, guys, k equals 0, so which is basically 3, 0, p to the 0, then 1 minus p to the 3 minus 0. So it is 3, 0, this combination. Do you guys know now what is the value of this combination 3, 0? What is the value of this combination? Factorial 3 over factorial 0 times factorial 3 minus 0. It is 1. Yeah, the value of this combination is 1. And p to the 0 is 1. 1 minus p to the 3 minus 0 is 3. So 1 minus p is basically p equals 1 half. 1 minus 1 half is 1 half to the 3 is going to be 1 over 8. Now we will have to find the PMF of random variable discrete binomial random variable x, which means that you will have to find the p sub x for all values of k here. So we'll finish this example in our next talk. Let's take 5 minutes break.